All right, welcome back everybody. This is the second video for section 6 of unit 3 of AP Calculus, calculating higher order derivatives. In the last video we introduced the concept and notation of higher order derivatives and looked at how to calculate a few of them, and then introduced the finding of higher order derivatives in implicit differentiation, which is a little bit more complicated. In this video we're actually going to just look at a couple of examples, 2 examples to be exact, where we're going to find derivatives or higher order derivatives using implicit differentiation. One where we're finding a higher order derivative, and one where we're doing one of my favorite example problems related to implicit differentiation. So here we go. Example 5. If x squared plus y squared equals 25, what is the value of d squared y dx squared at the point 4, 3? So we're finding the second derivative, so we're starting with the original function. So we've got to go ahead and take the first derivative, find the first derivative first. So we're going to go ahead and take the derivative of this. The derivative of x squared is 2x. The derivative of y squared is 2y dy dx. Since we're differentiating with respect to x here, because we're going to the dx squared. And the derivative of 25 is 0. So now I want to solve this for dy dx. I'm going to go ahead and subtract 2x from both sides, and divide both sides by 2y. And I'm going to want to go ahead and simplify that to the opposite of x over y. So there's my first derivative. And now I want to go ahead and take the second derivative by taking the derivative of all of this with respect to x. So the derivative of dy dx with respect to x is d squared y dx squared. And on the right hand side, I'm going to take the derivative of the opposite of the quantity x over y. I'm going to leave that negative sign out in front and take the derivative of this using the quotient rule. I've got low times the derivative of high. That's y times 1. Minus high times the derivative of low, which is x dy dx. Square the bottom gives us y squared. And then what I want to do is I want to simplify this, and I want to replace the dy dx with the opposite of x over y. Actually, you know what? Before I make that replacement, I'm just going to go ahead and simplify the numerator and distribute this negative sign in. So that gives me negative y plus x dy dx all over y squared. And when I substitute negative x over y in, it becomes x times negative x over y all over y squared. Now I have a choice here, and what I certainly can do is just go ahead and substitute this point in here and do the calculations. I'm actually going to keep simplifying this because I want you to get in the habit of being able to do that just in case. So I need to get the y out of this denominator inside the numerator, so I'm going to multiply both numerator and denominator by y, and that gives me dy dx equals, and then I multiply this term by y, that gives me negative y squared, and I multiply this term by y, and that gives me negative x squared, all over, and I multiply this term by y cubed. And now I'm going to go ahead and substitute the point 4, 3 in there, so I put 3 in there for y, and 4 in there for x, and 3 in there for y again. And it looks like when I do all these calculations, I get negative 25 over 27. And so A is going to be our answer. All right. Example 6 does not require a higher order derivative, but it is a great implicit differentiation application where we can talk about a bunch of fairly important concepts that, from earlier in this chapter. We're supposed to find points on the curve, 2x squared plus xy plus y squared equals 14. And in part A, we're supposed to find where the tangents to the curve are parallel to the x-axis. And in part B, we're supposed to find where the tangents to the curve are parallel to the y-axis. So we know with tangent lines, the slope of a tangent line comes from the derivative of our function. So the first thing we want to do here is find the derivative of this equation. So I'm going to go ahead and do that. The derivative of this is 4x plus x dy dx plus y times 1. That's the product rule on the xy. Plus the derivative of y squared, which is 2y dy dx, is equal to the derivative of 14, which is 0. We sort our terms, keep all the dy dx terms on the left-hand side, and subtract all the non-dy dx terms. And then we get dy dx by itself. And we end up with this as our derivative. Okay, now, in part A, I'm supposed to find where the tangents to the curve are parallel to the x-axis. So that means in part A, what am I looking for? In order for a tangent to the curve to be parallel to the x-axis is horizontal, what has to be true about a tangent line if the tangent line is horizontal? And that means that we need the slope of the tangent line to be 0. Okay, so, and the slope of the tangent line is dy dx. So in part A, we're looking for when dy dx is equal to 0. In order for this fraction to be equal to 0, that means the numerator of this fraction has to be equal to 0. And so I'm going to go ahead and set the numerator of this fraction equal to 0. And that's going to give me a relationship between x and y for points on this curve where the slope of the tangent line is 0. So I can just go ahead and solve this by adding y to both sides. And I get the relationship that y is equal to negative 4x. So for any point on this curve with a tangent line parallel to the x-axis, that means that these two green highlighted equations both have to be true. So we have a system of equations now to find the points on the curve where the tangents to the curve are parallel to the x-axis. So we just want to solve the green highlighted system of equations. In order to do that, I'm going to use substitution. I'm going to substitute negative 4x in here everywhere where there's a y. So I've got 2x squared plus x times negative 4x plus negative 4x quantity squared is equal to 14. And simplifying all this, it gives me 2x squared minus 4x squared plus 16x squared equals 14. Gives me 14x squared equals 14. And so x squared is equal to 1. So x is equal to plus or minus 1. I'm almost done with part A now. In part A, I want to find the points on the curve where the tangents to the curve are parallel to the x-axis. I've got the x-coordinates of those points. X-coordinate of one of those points is 1. The x-coordinate of the other point is negative 1. In order to get the coordinates of the points, I need to take these x-coordinates and substitute them back into one of the original equations from the system, either that one or that one. I'm going to go with this one because it's so much easier. Okay, so we'll substitute those x values in, we multiply them by negative 4, and bada boom bada bing. Those are our 2 points where the tangent lines to this curve are parallel to the x-axis. Okay, that takes care of part A. Now in part B, we want the tangent line to be parallel to the y-axis. Now if it's parallel to the y-axis means that it's vertical. So the slope of the tangent line is undefined in part B. In order to make this derivative undefined, that means I need the denominator of the derivative to be equal to 0. And that establishes my relationship between x and y in part B. I solve this for x because it's the easier of the two variables to solve for. I get x equals negative 2y. And now I'm back to I've got a system of equations with these green highlighted equations, the original equation and this derivative equation, and I want to solve this system. So I'm going to take the original equation and I'm going to substitute negative 2y into it everywhere where there's an x. And so that gives me 2 times negative 2y quantity squared plus negative 2y times y plus y squared equals 14. That gives me, let's see, that's 4y squared, 8y squared, minus 2y squared plus y squared equals 14. So 7y squared equals 14. Y squared equals 2. Y equals plus or minus the square root of 2. Again, those are just the y coordinates of the points. I'm looking for the points, and so I need to get the x coordinates for those points as well. Y coordinate square root of 2, y coordinate negative square root of 2. In order to get the x coordinates that go with those, I need to substitute back into this equation. And that tells me the x coordinate is negative 2 times the y coordinate. And bam, there are my 2 points that are on the curve, where the tangents to the curve are parallel to the y-axis. Now, imagine, if you will, this curve that we just saw. We've got, let me go back to this curve here, 2x squared plus xy plus y squared, 2x squared plus xy plus y squared equals 14, right? So let's take a look at that curve. And that's what that curve looks like. So when they're parallel to the x-axis, tangent lines parallel to the x-axis, goes through this point right here, negative 1, 4. That was one of the points that we found, negative 1, 4. And 1, negative 4, those are where the tangent lines are parallel to the x-axis. And then parallel to the y-axis, it's somewhere out here and somewhere out here. And hopefully you can see that that's happening at negative 2 root 2, which is about negative 2.828, almost 3. Root 2, which is about 1.4, so right about there is one of them, and the other one is the mirror image down here. So that kind of ties into what you've seen algebraically tied back to this graph. And now I lost my lesson. There we go. Sorry for the clutter on my desktop. All right, that's the end of this video on higher order derivatives, and then we saw that neat little application problem that tied to implicit differentiation. Had to show you that one. It's one of my all-time favorites. All right, see you next time, and actually next time we'll be starting Unit 4. We are done with Unit 3, so enjoy that. Have a great rest of your day, everybody, and I'll see you next time.